Thank you very much. My name is Sergei, and today I'm going to talk about the aircraft localization, about the station synchronizations, and so on. So as Martin mentioned, I participated in the aircraft localization competition in 2020, and I would like to talk about this a bit. But let's have a look about an agenda of my presentation today. So first of all, I will start with the competition itself, a brief discussion and what it was focused on. After that, I will touch some basics of aircraft localization, and after that discuss a few models which I developed for the solution. After that, there will be a chunk regarding synchronization of stations, which was the most complex part for me in this competition. And finally, I will talk about the aircraft track reconstruction, some mathematics around this. So first of all, I would like to thank the organizers of this exciting competition. It was held between 15 June 2020 and 31st January 2021 and consisted of 2 rounds. So I participated in both of these rounds. In the first round, I took just the 4th place, but on the second round, I was lucky enough to get the 1st place. And this presentation would be about the solution for the second round because it combines all the ideas and all the methods developed for both of these rounds. So the organizers of this competition were Open Sky Network and Seed Campus of RMSU Science and Technology, and the data was provided by Open Sky Network. So the goal of this competition was to identify unknown aircraft locations by station measurements. So why I think this is important, because new technologies of aircraft positioning are developing and deploying at the moment in different countries. And one of these technologies is called ADS-B technology, where aircraft can identify their location using different sensors, but also including GPS. And aircraft broadcasts his position so that that signal can be received by ground stations in passive mode. So they don't need to actively looking for aircraft. So they can just receive the signals, and this opens this allows the ground stations to use low cost or even budget sensors to receive the signals, combine this into network, and after that use to track aircrafts. And this idea is just another idea to use an ensemble of, for example, budget, low cost receivers, estimators, and sometimes in some certain conditions, they can even overperform the good stations. You know, sometimes if there are just a few stations, but they are really good. Sometimes it's the balance between the cost and accuracy. So that was the goal of the competition. And as I said, there were 2 rounds for this. The first round was mainly focused on the method of aircraft localizations, because all the stations were synchronized initially, and actually participants developed different methods how to localize aircraft, how to restore tracks, and so on. And the second round was mainly focused on synchronization of stations. So just a few stations actually were synchronized initially, and most of the stations experienced clock drifts. So the challenge was to synchronize all the stations in order to apply the methods developed in the round 1. And I would like to touch, of course, the both part of this method, so of these rounds, both rounds. So let's start with just aircraft localization. I will give just a brief overview of the methods which was used in this solution. So as you can see, there is an aircraft, and aircraft sending a signal about his position. And this signal is received by many stations located on the surface of the Earth. Each station have their timestamp, and their location should be known. So giving this information, we can use the famous multilateration technique and solving this equation, right? So we can identify location of the aircraft, or vice versa. For example, if we know the location of the aircraft, we can identify stations, locations, or update their location, and so on. So I will show different methods how we can apply this equation a bit later today. So in the equation, the variables are distances between aircraft and stations. There is a radio wave velocity, timestamps, which measured by stations, and a clock shift of stations. Even if stations are synchronized, there still could be a clock shift between them, so that we need to eliminate this time shift in order to apply this equation. You can see that this method is differential, so it does not depend on the aircraft actually, because we measure the same signal. We need just measurements detected by different stations. And just because of the geometry, of this experiment, we need to have at least 3 stations available in order to identify location of the aircraft. So 3 or more, 4 or 5, and so on. If we have just 1 or 2 stations, it's not enough information to get location of the aircraft. But we still know the timestamp. We can estimate location of an aircraft in post-processing. So particularly for the second round, I developed the radio wave velocity model. And I would like to explain why it's important. So in the first approximation, radio wave transmits in the atmosphere with a speed very close to speed of light. But if you use the speed of light in the equation, it will be a mistake. Because atmosphere has a refractive index, and radio wave velocity depends on the refractive index. So the closer to the surface of the Earth, the lower the velocity. I can compare 3 approaches how to model this situation. So the first approach is just at the beginning to use the speed of light. The second approach is to use the constant velocity. For example, if we look at the refractive index near the surface of the Earth and we calculate the radio wave speed, we can use this value, for example, or as was used in the round 1 of the competition by one of the competitor, he optimized the multilateration equation and found the optimum value for this effective velocity. So this is another approach, and the approach which I used in this competition, I developed the model which shows how effective velocity depends on the altitude of the atmosphere. So first of all, let's have a look what is effective velocity. As I said, velocity depends on the refractive index, so it depends on the altitude, and effective velocity is just average velocity along the wave path. So we don't need to integrate velocity like by time or any other variables. So instead, we can integrate this in advance and just use the final formula in order to estimate this effective velocity. As you can see in the numerator, there is a still speed of light, but there is a denominator which depends on the altitude of a ground station and altitude of an aircraft. The difference between these 3 approaches it was measured like the following. So the difference between speed of light and the constant effective velocity, which was used in the first round by the top 3 teams, the difference between this in terms of the accuracy of localization is about a few meters. So a few meters accuracy of localization. The difference between the second approach and the model, this model, is about maybe 10 centimeters, right? So you can see that the order is much lower. And why I think this is important, because the difference in accuracies achieved by the top 3 participants in the first round was actually about 10 centimeters. That's why, because of the competition nature, right, of the task, so I developed the model which potentially could improves a bit this part of the solution. The outcome of this model is altitude profiles. It was interesting that having the data provided by OpenSky and fitting this model to the data, we can restore actually how refractive index depends on the altitude. So you can see on the Earth, it's about 1.3035, right? And decreasing with altitudes up to 1.3015. So the difference is very small, but we can still feel this difference when we're solving multilateration equations, and this is very exciting. like the future application of this, I can see that it may be possible to use these signals to monitor like weather conditions, or for example, pollution near the cities. So it's quite interesting methods. Maybe it will find some applications in the future. But what is important for this solution is that now effective velocity depends on the altitude of the aircraft. And this gives some advantage, as I mentioned. Now let's talk about the synchronization of stations. In this competition, I was managed to synchronize 241 stations, which you can see this in the figure. Most of the stations were located in Central Europe, like Switzerland, Germany, Netherlands, and England. And there are other stations like in Ireland, in Portugal, in France, and so on. There were two types of stations. The red points denote on the figure the stations which were synchronized already. So they were equipped with GPS sensors, and we know their locations pretty well, and they did not experience clock drift, so they've got just a time shift. All the other stations, which are blue in this figure, so they experienced clock drift and they need to be synchronized. Now let's talk about the synchronization part. From the nature of the clock drift, so I would like to select two parts. So the two parts which are included in the clock drift. So there is a linear part, which linear depends on the time, aircraft time, and there is a random walk, which was modeled by just cubic splines, for example, right? Now, what does it mean, synchronized stations? It means that stations, if we know the aircraft time and we know what the time of flight, the station should measure just aircraft time plus last time of flight, right? So, and this should be true for all the stations which are synchronized or included in the network of the synchronized stations. So, having this in mind, we can see that the right part of this equation gives you a way how we can synchronize the measurements of a particular station given an aircraft time, right? So this is pretty straightforward. We've got a couple of parameters for linear regression, and we've got a spline. The question is how we can calculate the T aircraft. And T aircraft can be calculated only using synchronized stations. So we need to have a set of initially synchronized stations in order to synchronize other. And this gives us the process of synchronization. So we need to start with a set of initial stations, and after that synchronize every stations one by one using the station synchronized already. So after synchronization, we can include this station into our set and just continue synchronize other stations. Also, on this slide, you can see that if we have a drift, so the drift is actually the residuals, time residuals between T aircraft and measured time. So these residuals can be fitted by a linear regression first, so that we can identify parameters A and B here. And after extracting the linear component of the clock drift, we can fit a spline. And this gives us a random walk estimation. So I will show an example of random walk a bit later. Now, just a few words about synchronization of GPS-equipped stations. So as you can see in the multilateral equations, there are lots of parameters here we can optimize. So this is the position of stations. This is the two parameters of the radio wave velocity model. This is constant time shifts. Because we've got two data sets, training data sets and testing data sets, right? So we can use training data sets where locations of aircraft were known, and so we can optimize the locations of stations, parameters, and so on. Now, let's have a look at the random walk examples. Here you can see residuals. So the blue dots, these are residuals between T aircraft and T station, right? And after eliminating the linear part of the clock drift. So if we look at the right figure, we can see this is pretty good station. And the random walk is So you can see that the clock drifts for approximately a few microseconds for 1,000 of seconds of station time, right? So this is a pretty normal behavior. On the left figure, you can see unusual behavior of stations when the clock drift experience sudden change. So this is not the random walk. This is actually the linear drift, but it was considered as a random walk by my algorithm. So you can see that the magnitude of clock drifts is quite different. So if we consider a time interval of about 1,000 seconds, the same interval, we can see that the clock drifts for a few milliseconds, so 3 orders more. That's approximately the orders of magnitude for linear drift and the random walk, which stations experience in this experiment. Now let's go to the aircraft track reconstruction. There were mainly 3 steps in reconstructing tracks. So first of all, aircraft localization were found in points using multi-iteration equation. In this case, after having all these 241 stations synchronized, we can easily do that. After that, we would need to filter the points using, for example, the graph-based filter developed in the round 1 by Richard Alligier. The third step was about adding points where the number of available timestamps were less than 3 or they were outliers. Here, I would like to just focus on the graph-based filter. On this slide, you can see that there is an aircraft track consisting of several points, and there is a location outlier. So something happens here with the signal, we can see it as an outlier. So this algorithm actually looking the distance between consequent points and calculates the aircraft velocity. And if aircraft velocity exceeds 300 meter per second, this means that, this is outlier and we don't need to consider this point. So instead, we can use the link, which is denoted by the green arrow here, and just continue this aircraft track. It was surprising that this algorithm, pretty simple algorithm, but at the same time, it was a very efficient one. And I used this in the second round as well. Sorry, coming back to one slide. What was the result of all these techniques? We can see that I managed to predict 71.8% of aircraft locations in the test data set with accuracy about 85 meters. So this is root mean square error in distance accuracy. So because of the competition nature, again, of this task, of course, I was looking for ways to improve this accuracy. And there are 2 main ways how we can improve here. We can remove points with large errors and we can add points with low errors. But anyway, we would need to find a way how we can estimate the prediction error. And this method was developed by me. And the method was based on the 2 reconstruction approaches. So after we have aircraft localization in points, so we can use this as a reference. And after that, fitting these points with different techniques. So there were 2 techniques which I used. One was based on the just cubic splines, and another technique was based on the Huber regression technique developed also by me in the first round. The idea of this technique is that in some time location, about 1 minute, right? So I estimated latitude and longitude of the track. As a polynomial regression by time. So latitude and longitude changes like a polynomial by time, and I fitted all the points around this particular point using these polynomials. And this gives me an alternative technique. So I can compare predictions provided by these 2 techniques and estimate the distance between predicted points. And this distance gives me estimation of the prediction error in certain points of the track. And why this is important, I would like to show you on the next slide. we look at the reconstructed track, so you can see, for example, on the left figure is pretty good track. So this is an aircraft, and everything fitted well here. But on the right, on the right figure, you can see that this is a small aircraft, and his trajectory is very sophisticated. This is probably the one from general aviation. And the algorithm should be very robust in terms of what it predicts. So having two approaches and having a method to estimate the accuracy, the prediction accuracy of the track is very important to eliminate points where we are not sure about the location of the aircraft. So this is briefly all my work, and thank you for your attention. Please, if you have any questions, I will try to answer them. Thank you.
Perfect.